I was doing Burger's equation. So, let us just write this again. So, it is in 1D, okay. And I told you what to do in the last class. You can use Runge-Kutta second order for this and higher order for this. You can use, I mean, you will be working on a small grid, maybe 100 points. So, it will not take too much time. So, use higher order. In fact, for this also you can try to use higher order and not use upwind. Upwind you have to put if condition and so on. So, try higher order, maybe RK4, and then higher order means you will need. So, if you use fourth order, then you need 5 points. So, you can use 5 points. So, try to play around with it. So, okay. I also discussed what should be a time scale, delta t. So, one time scale comes from h by u max, right. Another time scale comes from this. Now, I did not tell you what this is. This is called kinematic viscosity. Okay. So, this is so in StatMech you might have done estimation of this kinetic theory, maybe not, but you can estimate this from. So, this because a higher speed fluid moves on a smaller speed fluid. So, if there is a layer of fluid with different differential velocity, then there is a friction, and that friction, in fact, this is a friction term. Now, it has dimension of nu has dimension of length time velocity. You can just check. So, u cancels. So, nu has dimension of length, this u cancels, and you will find that nu has dimension of length and velocity. It is very important thing to know. So, it has units of centimeter squared per second. Okay. So, one time scale will come from here is s squared by nu, and we also seen that delta t must be less than s squared by nu divided by some factor. So, that is CFL condition. So, CFL, there are 3 mathematicians. So, this Courant, Friedrich and Levy. Okay, so, this is what I saw that. So, Courant is a very famous, Courant and Hilbert, there is a book on mathematical methods. So, they have been working on it for, I mean, this condition is named after them. So, this for delta t. So, use minimum of the two. What about delta x, or what should be your h? So, h is again, so I am going to use this dimensionless this number nu. It will depend on nu, because nu, in fact, this determines. So, in the shock, if nu is 0, we will get this. As soon as we put nu, there is a dissipation. So, here the gradients are sharpest. So, the viscosity will be most effective in this region. Right? There is a the derivatives are really very steep. So, because of viscosity, the profile looks like that. It smoothens. So, this will be function of nu. So, again I would make an estimate. I have not done this problem myself, but I would make an estimate delta x h is nu by u max, right. So, it has dimension. So, I need dimension of length. So, nu by u and u max can be a good estimate for h. Now, for your code, so now once so I need to also give you the initial condition. So, initial condition for this, so box size I would choose 0 to 2 pi and make it periodic. So, the shock will move and come back like that. Okay. So, make it periodic, and the initial condition I recommend use sin x. There is amplitude u max is 1 in the beginning. You can play around with this, make it half, the code will try to, well, in fact they will tend to blow up. So you make in the beginning, when you test it, you make it 1/10. So initial profile will be like this, and where will shock appear? Can you make a guess? So these are the fast moving cars, the fastest, slow, and this is negative direction. So shock should appear somewhere here, because this fast guys will go ahead and they will jam on this slow moving cars. So the finally you expect something like this. Okay. So this Burgers equation you can get started and do your simulations. Now more general equation than this is called Navier-Stokes for fluid flows. This also is a fluid flow, but I will contrast what I am going to write here with this in a minute. So the equation which is written for fluid flows is, so there is a velocity field, it is a continuum. So in this room the gas is specified by equation which is, we assume it to be continuum. Okay, there are molecules, but we look at scale where the molecular my length scale is much bigger than the mean free path length. So there will be probably 1000 molecule in one packet I am thinking of. So my x is not position of molecules, but x is position of a fluid parcel which is averaged of around 1000 odd molecules. Okay, this is called continuum approximation. So I have to make continuum, otherwise I will be dealing with molecules and atoms, and this too many of them, this too tiny scale, not a good idea. Okay, so fluid flows, the equation is, so there is a velocity field u. So equation is u dot I am making an assumption that density of the fluid is constant. It is good for water, not for air, but okay. So we assume that density is constant. Okay. So P is the pressure and nu is the same kinematic viscosity. Okay. Now this is not my job to derive this. You can, if you have not done it, you can look at Wikipedia and see the derivation. Now, so rho equal to constant gives you a constraint that del dot u is 0. Okay. So this is the equation for incompressible fluids. So this is called incompressible. So we can't compress it. Okay, so how do you solve this one? So there are two methods which I have given as projects. So one thing is called spectral method, other one is finite difference. There are more like finite volume, finite element, but we just focus on these two. So let me first do spectral first. Now spectral I will assume something and I will do only part of it, but I will do later part. Fourier transforms we will do later, how to really compute it, but I will just give the definition which you know from your earlier courses. Okay. So so for this equation I said use periodic boundary condition. Okay. So for this also project specifies that you use periodic boundary condition, it is easier to implement. So we will use periodic boundary condition. For periodic boundary condition, it is a good idea to use the wave basis functions u of x exponential, no, you do I k x not sine. So u k, so these are 3D vectors. Okay, this you know, but since I am doing in a box, these are sum, not integral. Now if the box size, this in quantum mechanics I am sure you have done this. So, Lx, Ly, Lz. So, my k vector is nx by Lx 2 pi and ny by Ly 2 pi nz by Lz, right. This is same as that Brunois lattice in solid state physics. So, instead of thinking in X space, I can think in Fourier space, but Fourier space things are discretized. I do not get values at all k's, but I get only at these k's. Nx, ny, nz are integers. It can take positive and negative values, right. So, these are the definition of Fourier transforms. So, instead of x, y, z, we have this, there are grid points like this. Now, so I do not want to solve ux, but I want to solve uk. So, that is spectral method. So, I did mention for diffusion equation you solve for temperature k of phi k. So, here I will be solving for uk, u hat k, hat means Fourier transform. So, I will convert this equation in Fourier space. Okay, so, let us rewrite this equation a bit in terms of tensor notation. Is better. So, I am going to rewrite this equation for a component. So, let me call that component ui. So, I can take index from 1 to 3, which means x, y, z. So, you know how to convert this. So, the idea is to, there are many ways to do it. You can substitute that equation here. So, I am going to show you only few terms, okay. I will not do all of it. So, let me first write down in real space for ui. So, ui is this partial t plus a second equation I am going to, so this equation is, this term is del j uj ui, some more j's, but this Einstein notation where if the repeated index means already the sum. So, this really means u1 del 1 ui and ui is either ux or ui or uz. Now, since what is this condition correspond to in Fourier in terms of tensor notation? This will be del j uj is 0, right, del x u x del y del, so is. Now, I can use these here to write this as, I can push this uj inside, right, yes, because let us do some rough work here. So, del j uj ui is uj del j ui chain rule plus ui del j uj. So, this is 0. So, this is exactly same as what I got there. So, I can write this term as del j uj ui. So, I am pushing uj inside. Now, pressure is minus del ip and viscous term is nu, is written as del j square ui or del j j ui. Okay, so there is no, well, I mean I can write like this. So, double derivative. So, partial x twice plus partial y twice plus partial z. Now, when I do the Fourier transform, so I had to substitute this inside. So, in terms of indices, this is going to be I and I. So, when I substitute it here, del t will act on, no, by the way, please remember that this is function of time and I want to evolve this in time. This is only function of x. So, all the time dependence is here. My velocity changes with time, my Fourier coefficient will also change in time. So, this also has time dependence. So, if I take the time derivative, what will I get? This nothing happens to this. So, I will get u I hat, not total derivative, no partial, because the only function of time. K is a name for this. So, at this point there is a variable u k, but now how does it change with time? Now, there is no partial of u with k, it is a discrete variable, no, u of k is discrete position. So, this is of k t. Now, let us look at this equation, this term. Now, minus the partial will act on what? It will not act on this, but it will act on this. So, what will it give us? Partial I k. So, always take an example. So, I am doing partial x of p. So, p is also Fourier transform. So, p will be, so there will be sum p hat of k t power I k dot x. So, this means k x x plus k y y plus k z z, and I am going to act partial on this. So, what will it give us? So, this is k x x plus k y y plus k z z. So, only I k x, this is silent, I mean in fact 0. So, I am going to get I k x outside for I k dot x. So, each time we do partial derivative I get k I k out. Now, this you might have seen from the property of Fourier transform. So, each time I do Fourier transform I get I k k I p hat integral. This I should write okay, and not integral, sorry, sum. So, we have to do it like this for all the terms. So, here I get minus I k I p hat. What about this term? So, if I do the derivative twice, so I will get I k twice. So, I k times I k x times I k, it becomes minus k x squared. I have to do also for partial y squared. So, that will give me minus k y squared. Then when you do for partial z, the minus k z squared. So, this gives me minus k squared. Okay. Is that clear or not clear? So, everybody knows, no, Laplacian means sum of these three, dy square plus d. Okay. So, I'll keep getting this. So, to multiply by minus k squared for here, minus nu k squared u I hat of k. What about this term? What do I do with that? Plus sum. So, let us assume that this is a f, some function f. Okay. So, partial j of f. So, what is partial j of f? I k j f hat of k. Now, this function of j and I both. So, this should be really written as j I. Now, so I k x is common in all of them, yes. So, since ikx forms a complete basis, so coefficient of an orthogonal basis, they are orthogonal basis. So, what should happen to the coefficient of ikx, and this is true for all x, this is true for all x. So, that gives me du hat of k dt plus ikj Now, I am still I do not know how to compute f at k. Now, please remember this is the product of two functions and the product's Fourier transform. So, if there are two functions uj, well, let me call it function, I already use f, gh, g of x and h of x, its product is f, Fourier transform of this is what in terms of Fourier transform g in h. I am multiplying right now in real space. This is really gx, hx, so what do I get from theory of Fourier transform? It is a convolution. Okay, good. So, f hat of k is g hat of p h hat of k minus p sum over p's. So, this is this theory. Okay, now you can prove it. I will leave it as an exercise. In fact, it is interesting exercise to prove this using just property of V do ikx. Okay. Now, so basically given my velocity field, I know all these terms because I can compute by convolution f at k. Yes. So, now I can use Runge-Kutta or Euler scheme to integrate this. I am not integrating u of x, I did not discretize in real space, please remember. I am working in Fourier space and these coefficients are changing in time. Now, I can solve this as function of time. So, you can easily write u hat of k dt is r of k. Everything I take it to the right hand side and this is r of k for every k. Now, of course, there are lots of k's, but there are how many k's will be there? I will, so number of nx, number of ny, number of nz. So, that many products is a 3D grid like that solid state physics, you have all the grid. In principle, it is infinite of them, but we will cut it off and I will tell you how much you should cut off. Is that okay? And by the way, nx, ny, nz all go from real to imaginary, I mean sorry, minus infinity to plus infinity. So, this you can solve now Runge-Kutta method, you can like Runge-Kutta second order, you can easily do it, and so this is spectral method. Okay. So, I will give you a real initial condition. Okay. If you like, I can give initial condition in the Fourier space itself. Now, so or in real space you can do the Fourier transform, but you have a very good interesting point. Is pressure independent variable? Because I do not have any time evolution of pressure, right? There is no dP by dt. So, how do I compute pressure? Okay. So, I can use this constraint to derive an equation for the pressure. So, I will do little bit of algebra, but so let us take the divergence of this equation. So, I think it is better to work out here only. So, if I take the divergence of that equation, what will I get? So, if I take divergence, what happens to this term? So, remember divergence u is 0. So, d by dt and divergence commute. So, partial x and partial t you can do it. So, if I take divergence of this, the first term is 0, second term is not 0, okay. Second term divergence of u dot is a scalar quantity. What happens to divergence of this? It becomes Laplacian. Divergence of gradient is a Laplacian. So, Laplacian of p. And what happens to this? So, you can show easily that the Laplacian and divergence commute. So, I can push the divergence inside and this term also is 0. So, this is 0. Now, what is this equation? Laplacian p is some function. So, this is a Poisson equation which many of you are doing as a project. So, some of you will need this in your solvers, okay. For finite difference, when I am going to come to it, you will need this for your solver. So, this is Poisson equation. Electrodynamics, no. So, divergence of Laplacian of potential equal to minus sign or no? Minus. In fact, exactly same equation. So, if somebody gives you this solver, then you can solve this one. You just have to compute this f. It is like charge density. So, you need one tool which can be applied in various places. Precisely. For spectral solvers or for this method, this is straightforward. So, if I do the Fourier transform of this, what will I get? So, Fourier transform this. So, left hand side will be divergence gives you I k dot, okay. So, divergence is I k dot, I k dot. Now, this is a nonlinear term. So, I just use a shorthand notation n hat of k. You do not need to compute again. Suppose you already computed here, this is a nonlinear term, you can recycle it. You do not need to compute this quantity again. It is exactly same what is this term, okay. Now, what is Laplacian of this? Minus, I already showed you Laplacian is minus k squared, right, Laplacian minus k squared. So, minus minus becomes plus k squared e hat of. So, if I know the velocity, I can compute pressure. This is part of incompressible assumption. Pressure is not an independent variable, pressure can be computed given velocity, okay. Now, it has major implications, but I will not discuss that, but given the velocity. So, I will give initial condition as velocity only, and you have to make sure that velocity is divergence free. So, I would recommend if you are trying to solve this method, then you can start with some components of velocity field in the Fourier space itself. You do not need to start with real space. So, what should I use my initial condition? So, I recommend that let us use 1 1 1. Now, it has 3 components. So, but I have to make sure that I erased it. My k dot u k must be 0, divergence free condition. So, what is kx for this? So, I can say nx is 1 and I am using 2 pi as my box. So, use 2 pi box. So, 2 pi cancels. So, my k becomes basically nx, ny, nz, clear. So, that is why it is convenient to use 2 pi box. So, I am going to use, so it is 1, so I will make uz 0 of this, and I have to just make sure 1 multiplied by this and 1 multiplied by this must be cancelling each other. So, that means if I use this alpha, then this will be minus alpha. So, you can choose alpha as 0.1 and ui must be minus 0.1, that is it. So, you can start with this and you simulate it. Now, there is only one more catch. So, is that clear to everyone? It is not such a simple method, but you have to just do bookkeeping, and I will give one reference, 2 pages, you can look at it and you can code it. Now, do not look for very efficient solution, I mean just do simple solver. Now, my velocity field is real, right. I mean I always have worked with real velocity field, it is not complex. Now, if this is real, then this is some condition the way number, this uk hat k. Now, it is quite easy to check. So, what is the inverse transform of this? So, I can invert it, is integral of ux or minus I k dot x divided by volume and so on. That is an inversion. Now, what about u star of if I take the complex conjugate of this, what will I get? Same thing. Now, this becomes I plus k dot x is a complex conjugate, but if I put minus k here, then what will I get? Minus here. This is exactly same as this, since ux is real. So, there is no complex conjugate of this, that means these two must be equal. So, not all the Fourier modes are independent. So, in this 3D cube, so if let me just draw in 2D, it is easier to represent. So, if there is a vector k, there is a Fourier transform here, in the opposite direction here it is complex conjugate of this quantity. So, you have to make sure that this is complex conjugate, otherwise your real velocity will not be real, not guaranteed to be real. So, we save only the upper part, you do not save the bottom part. So, I would recommend that people who are doing spectral method just do for 2D, do not work with 3D. And this part, so problem is if you save it only upper part, then this part is not, you are not saving. So, there is guarantee that this part will be complex conjugate. I am not even saving it. So, I will assume that if somebody asks me what is the Fourier transform of here u hat k, I say this complex conjugate of this. Now, my only catch is that this part must be complex conjugate of this part, right, and that you have to do by hand. This part, look, what is the minus k of this? So, if this is k vector, minus k vector will be here, which I am already saving it, no. So, this part you have to be k. So, there are some care is required when you write these codes. So, please work in 2D, do not work in 3D, and you just take care of this part. Now, how much grid size should I choose? Now I will give the theory, but you should work with viscous flow. So, what is viscous flow and what is turbulent flow? That let us just little bit talk about it. So, something called Reynolds number, so which is defined as velocity u RMS, you may call it, times length divided by viscosity. Okay. So, velocity I can compute u RMS of the full box, length is 2 pi and viscosity will come from here. Now, the grid size is chosen from this for Reynolds number much bigger than 1 is turbulent regime, and here the grid size n in each direction. So how much nx should I choose? So the max value of nx will be 3/4. That is the formula. Okay, that formula comes from some theory. Now if you want Reynolds number of 10,000, okay, suppose somebody tells you that okay, I want you to simulate Reynolds number of 10,000. So what should be n for this? So if Re is 10,000, so 3/4 of this 1000. So 1000 in each direction, so that makes it 1 billion points. Okay, now 1 billion point is very difficult to simulate even in ordinary computers, ordinary supercomputers. It definitely won't work in your PC. So this is the complexity. So you become 1 billion points. So you can see how much time it will take, how much memory is required, all that computation comes. So for you, you should not work in this regime at all. Your Reynolds number must be maybe 1. It is a viscous flow. So I would recommend that you put viscosity 1, U as 1 and L as 2 pi. Okay. So your initial condition will kind of give you the velocity estimate. Okay. So U squared, this square plus this squared is the kinetic energy. What is kinetic energy? By Parseval theorem. The Fourier transform is very useful. So what is Parseval theorem? Has it been done Fourier transform in your course sometime? So Parseval theorem is integral U squared x dx by volume. This is sum of, okay. So I want this is an energy, average energy of the whole box. So I just mod square of this. So it will give, and from that you can compute URMS. Okay. So this calls pseudo spectral. Well, this is spectral method. Now I have one more catch, very important catch. How to compute this f? Because I need to compute this one. Very good, very good. So suppose I have 1 billion points. Okay, now this is not uncommon, we do this simulation. If Anando is doing 4,000 cube simulation, so that is 64 billion points. Okay, that's really huge. That's a record for these kind of flows. So, but even 1000 cube, how many multiplication will be required for 1000 cube? So this is P. For each k, I have to do that 1 billion operations, n cube operation. Is that clear or not clear? For each k, I have to sum over all p's, and how many p's are there? N cube points. Now I have to do this for every k. So how many operations I have to do? N cube squared, n power 6. So this requires operations n power 6. Okay. So for one convolution of this operation, it is, so let us 1000 cube. So billion times billion is 10 power 18. So 10 power 18, no computer in the world right now can do it in finite time. I mean, it will take maybe like 10 years. But there is a very neat way to overcome this. One very nice way to do it is called fast Fourier transform. So not just Fourier transform, but you do fast Fourier transform. The fast Fourier transform is, okay, first what is fast Fourier transform? So this is a definition. How many operations does it take for each k? I have to do this multiplication. There is a multiplication here is order number of points is again n cube, and I have to do for each x. So just imagine the number of x used is n cube again. So this is called discrete Fourier transform. So, this is what I will do bit later. So, this is discretized in a K space, but I also discretize in real space. So, there will be n cube. So, I will make this point clear, but we will do it maybe. So, let us do. Now, there is a theory that number of K point must be same as number of X points, otherwise you cannot really invert the matrix. So, number of X points must be same as n cube. So, this is required for n cube, and every point I need to do n cube operations, again this n cross x. So, this again practically impossible. So, there are two clever guys, Cooley and Tuckey, Cooley and Tuckey. So, what they did was they devised a very clever scheme, which I will not do the algorithm. So, instead of order n squared, if n is the number of points, let me call it m squared, m is n cube. Instead of this, it takes, instead of m squared, it takes m log m. Now, intuitively speaking, the idea is to convert into sum of real part, even and imaginary, even and odd parts. So, let us say I have 8 points, 0 to 7. So, I am doing the sum over all of them. The idea says no, do not do that sum, take the even ones in the left and odd ones in the right and combine the two. Okay, that is the idea. Now, you can see that if you do it again, you convert these into even and odd. So, this is 2n. So, 0 to 7 I am going to bring here 0, 2, 4, 8 and 1, 3, 5, 7. Now, here I just factor 2 out, so I get 0, 1, 2, 3, 4, then again divide it even and odd. This again you take 1 out, then do even and odd. So, you do it recursively. So, this is called divide and conquer. So, divide each time even odd. So, tree you go down is not n but log n, and that gives you log m factor. So, this is bit of working out, and you can write this algorithm, it is not difficult, but we will not do in this course. So, by FFT you can do it in m log m. So, fast Fourier transform is, we never do FT in computer, we always do fast Fourier transform, like Python will do fast Fourier transform given the data. Now, once I know this, then I can compute this using FFT. So, how will I do it? So, now this is easy. So, I need to compute this one. Please remember that I have ui of k. So, from ui of k, so all of them. So, I am working in Fourier space. So, I have ux of k, ui of k, and uz of k. So, I do inverse transform, I go to real space by FFT, fast Fourier transform, not FT, fast Fourier transform, then I go to ui of x. How many operation will it take? M log m. M could be 2d is n squared, 3d is n cube. Okay. Now, I multiply here in real space, point by point multiplication. So, this is what I need to do. How much operation will it take? I just, not m squared, this there m squared m points. So, you will just take m operations. I mean, you square the marks of your course, then you just number of points. So, this requires ui uj multiplication requires only m points, m operations. Well, I should really do a next step. So, this I can do ui uj, this m, then I can do in forward transform. From this real space I can go to forward transform, but I have quite a few of them. How many of the ui uj's are there? So, ux squared, ui squared, uz squared, ux ui, ux uz and ui uz, there are 6 of them, right. So, it is a symmetric matrix NC2 or 3C2 is 6. So, there are 6 of them, but each of them I do Fourier transform, I get dy uj hat, and how many operations will it take? Again m log m, 6 of them. There is a factor in front, now this factor of 5. So, this 5 times 6 is 30. So, instead of n squared I am able to do this in m log m, which is large saving. Now, if you have 10 power, we have 1 billion points. So, this gives you 1 billion, but this gives you 1 billion log 2. So, 10 power 9 so log 2 of this, which is something like 18, right, 9 times 3, 18 versus 10 power 9 is a big factor. So, it is possible to do now all these simulations on 4000 cube because of FFT, because of this people 1956 I think. Okay, so, these are clever schemes which we can exploit to solve fluid problems. Now, these were okay, I think I have covered everything. So, your number of points is, if you are doing in viscous flow, you can use maybe 100 points should be enough, 100 squared, which is already, I mean your computer will cry, you know, this like 100 squared is not going to be easy, but it will do it. Python is slow. What should be delta t? Now, if you use RK2, delta t again you can use the same idea. There is a time scale coming from here and time scale coming from here. So, it is delta x by u max and delta x by delta x squared by nu. So, take mean of this. So, what we did for burgers is very similar. Now, I have only 1 minute left. So, this is a project, anyone taken for compressible flow? Compressible. So, this for incompressible, you can also do Navier-Stokes for compressible fluids. Now, if nobody has taken a project, then I will not spend time on it, but you have more variables, you do not need to satisfy this condition. So, we write down equation for velocity field, which is already here, plus another term is there. Okay, there is a new like this. You have to write equation for density. So, there is equation for density and there is equation for energy, kinetic energy, well no, internal energy. So, that is proportional to temperature. So, you write down equation for density, velocity and temperature, and pressure and temperature are related. You can use ideal gas, and so you have 5 equations plus 1 equation of state, which is, let us assume ideal gas, and we have, so 6 equations, 6 unknowns, 3 velocity components, density, pressure and temperature. Okay. So, if nobody is doing the course project, it is okay, fine. What about MHD equation? How do you solve it? So, basically you have to again apply the same condition, del dot u and del dot v is 0. So, in fact you do not need to use this. If you do, this is used for computing pressure. So, you have to write equation for B, and B in Fourier space will be some equation like this. Okay. So, you have to convert this in Fourier space, and you have to time step all the components of U and all components of B. But pressure will come from this equation, except MHD has one more term, there is B dot grad B term. Okay. So, there will be minus, okay, so there is minus B dot grad B. So, MHD you can do it with the same technology. Okay. Now, I have to do for finite difference, maybe I will do in the next class how to do finite difference of this equation, Navier-Stokes. So, this is using spectral, we can solve it using finite difference as well. Okay, I will stop.